All right, so looking at graphs of gradient functions, it's actually a bit of a fun topic is you get given a graph and you have to think about what the gradient of that graph would look like. So if we start here, the key to all these questions is to think about at any point on the original graph what the slope of a tangent line would look like. So this green line here is clearly a constant function like y equals 2 or y equals 1 or something like that. And so hopefully you know that the gradient of a line like that is 0 always. The gradient is always 0. So in terms of graphing the gradient function, well, we need to graph a function where the value of that function is always 0. And hopefully you're recognizing that that's going to be a horizontal line on the x-axis. So it's going to look like this. So and that should make sense. If you differentiate a constant function, you get 0 as your answer. So this red line is the derivative of the green line. All right, so what we'll do is we'll just go up in the powers. So at the moment, we've got a constant function, which is x to the power of 0. So let's look at x to the power of 1. So if we look at this example here, before I give it away, we've got this green line. And this green line, hopefully, if you think about a tangent at any point, you think about the gradient of this line. Hopefully you realize that it's always positive, but the gradient doesn't change. Gradient is always positive, and it stays the same throughout. So the gradient looks like this for this function. And then so our job is to graph the gradient function. Well, if this number is positive, might be positive 2 or positive 3, but either way, the gradient function will look like this because the gradient doesn't change, but it is not 0 anymore. It's positive now. Okay, and then we can just keep going. So that's x to the power of 1, aka a linear function. So the next thing we can look at is a quadratic function. So if we've got something like this, something that has, the leading term being something x squared. Okay, now what we can do is think about, the slope of a tangent line at any point. Up here, the slope of a tangent line is negative because it's sloping down this way. And if we keep going, we're going to see that, it's still negative, but it's getting smaller. So it's negative, negative, but it's decreasing. So the gradient is decreasing along here until we get to this point here, which is a turning point where the gradient is equal to 0, at which point the gradient becomes positive. So we're going to have a small positive gradient to the right of that turning point. And then the gradient, as you can see, is going to get more positive as we get further to the right. So have a pause, have a think about what the graph of the gradient function here might look like. Hopefully you've had a think, and what we can do is we can graph it. It's going to look something like this. Okay, so when you differentiate, or you find the gradient function of a quadratic, it turns out to be linear, and that should make sense. When the x values are over here, say, you've got a large negative numbers, which corresponds to a large negative number on the gradient function. Here, at the turning point, the gradient is 0. That's why it has to be an x-intercept. So at this turning point here, the gradient is 0, so that must be an x-intercept. And then to the right, say over here, we've got large positive values for our gradient. So that's why, the red line goes off to positive infinity because this gradient keeps getting steeper and steeper. Well, hopefully you're getting the idea in terms of how these questions work. Let's look at something like this. So the next one we do is x cubed. Let's see what that might look like. So again, think about the slope of a tangent line. It's going to be positive and large down here, but it's going to be decreasing in this case. Still positive, but decreasing until it gets to 0 at that point there. And then it's small positive and getting bigger positive. Okay, so that's yeah, that's how we can think about the gradient. So then the next part is to graph the gradient function. It's going to look something like this, and we'll explain why it looks like this. Okay, so you graph the gradient function of something that's cubic, you get a quadratic, and that should make sense. So again, x values down here are large and positive, but they're decreasing. So they're coming down like this. So your gradient values are decreasing. until you get to this point here, which is what's called a stationary point of inflection. The gradient at this point here is 0. So that has to correspond to an x-intercept. Okay, so that's going to give you a gradient of 0 at that point. And then the gradient of the green line slowly increases. So the red line increases in that fashion because that's the derivative. All right, hopefully making some sense of it. We'll just do a couple more. Now we've got a different kind of cubic, and there's a few interesting things about this as well. So if we again play the same game with the signs, the plus and minus signs, we can see that it starts off as large and positive gradient, gets smaller, 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 until we get to this turning point here, which has a gradient of 0. And then you can see between these two turning points, between here and here, the gradient's negative, and it starts off small negative, and right there it gets to maximum negativeness, okay, which is going to be important for when we graph the gradient function. So it's getting to maximum steepness in terms of its negativeness there. And then it gets smaller, 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 it gets to 0, and then becomes positive, and it's increasing positive gradient from there. All right, so when we graph the gradient function, we know that at this turning point, we must have an x-intercept, and at this turning point, we must have an x-intercept. And we can see that this point here, where it gets to maximum negativeness between the two turning points, is what's called a non-stationary point of inflection. So that actually has to correspond to a turning point on our derivative function. So you'll see what that looks like now. Again, starting from the left, starts off as positive, large and positive, gets to 0 at the x-intercept there, gets to maximum negativeness at that non-stationary point of inflection, and then gets to 0 at the next turning point again, and then goes off. The gradient increases in the positive direction from there. So this quadratic, sorry, not quadratic, this cubic is actually going to dip below the x-axis because you've got a negative portion for the gradient in between the two turning points there. Okay, hopefully getting the idea. Let's just do one more that's a bit trickier. So this one here is a quartic, and now it's just getting tricky. Hopefully you've wrapped your head around the idea, and now, yeah, now you can start to think about how it works. So again, large negative, decreasing, large negative and decreasing gets to 0. All right, what's the stuff that's going on here is a bit tricky. So we'll just do our best to wrap our head around it. If it's going to become small positive gradient there, it's increasing a little bit, and then it gets to maximum positiveness about there. And it starts to decrease again, if you'll notice, in terms of its steepness. And then it gets steep, it gets less steep, and it's getting almost to 0 gradient there. Almost to 0, but it's still positive. It's not quite 0. And then it starts to increase positive again. Okay. And so if we graph that, it's going to look something like this. Starts off negative, so it's starting below the x-axis. All right, at the turning point, it's going to have an x-intercept, and then we've got a bit going on here. At that point where it gets a maximum positive gradient, it's going to be a turning point. So about there somewhere, maximum positive gradient. Then it decreases again, gets to minimum positive gradient around about there, and then goes up to. Then the gradient just keeps increasing. So it looks like that. All right, hopefully getting the idea. Last one. So I wanted to do one with a bit of an asymptote. So this graph here, if you're curious, is something like log base e of x minus 2. So it's log e. It's basically been shifted 2 to the right. That's why I've got an asymptote here. And so again, just think about the gradient. It's going to start off, we're going to start off as positive. We're close to that asymptote. It's going to be a large positive gradient. But that gradient's getting smaller and smaller and smaller and smaller. And it's almost, in this part of the graph, the gradient's getting very close to 0 because it's almost plateauing. So the gradient's getting very small. Okay, so maybe pause the video, have a think about what the graph of the gradient function will look like. Basically, it has to start very positive, and then it has to decrease to 0. So hopefully you've had a pause, you've had a think what the graph might look like. Hopefully you came up with something like this. Again, it starts near that asymptote. It starts as very large positive numbers, and then it decreases as x gets really large. The gradient values get really small. They get close to 0. So you can see that you're going to have an asymptote at y equals 0 along there. This graph of gradient of this green line will never get to 0, but it'll get close to zero. So you get something like this. Okay, if you're curious, yeah, we said the green line was log base e of x minus 2, and this red line, if you're curious, is 1 on x minus 2. So yeah, that's the gradient function. So hopefully you're getting a feel for how to graph the gradient functions. Yeah, hopefully that helped. Good luck with your studies at the moment.